Welcome back, Physical Science 20. This is part 2 of the HT1.4 video. So we had just labeled these graphs here, looking at the 3 different phases and the transition phases at those plateaus or flat lines. The temperature remains constant during those flat lines, those changes in state, because instead of moving energy, thermal energy is being changed into potential energy. So indications of change in kinetic energy or moving energy occur at temperature changes, but of course there's also another energy at play here, potential energy. So some of it's being changed into potential. On the heating graph, this occurs when solid changes to liquid and when liquid changes to gas. On a cooling graph, it's when gas changes to liquid and when liquid changes to solid. And of course those are the flat parts of the graph. The heating graph shows distinct melting and boiling points. The cooling graph shows distinct condensation and freezing points. The melting and freezing points are both 0, and the boiling and condensation points are both 100. In general, melting and freezing occur at the same temperature, and boiling and condensation occur at the same time as well, at their same temperatures as well. You may believe that temperature of a substance should change while it's absorbing or releasing thermal energy because thermal energy affects kinetic energy. But why does the temperature not change during melting, those transition phases? So kind of look at a reason here. During melting and boiling, thermal energy must be absorbed by the particles of a substance. This absorbed energy is needed to break the bonds that hold the particles together. However, during condensation and freezing, thermal energy must be released. The released energy now allows the particles to move closer together and become more organized. In each of these situations, the change in thermal energy of the substance results in a change in potential, not kinetic energy. Because remember, temperature is a measure of kinetic energy. So if we don't have kinetic energy being affected, and yet we're still adding or removing energy, it must be affecting else. In that case, it's potential. In other words, when a substance melts, boils, condenses, or freezes, the absorbed or released thermal energy is being transformed into stored or potential energy. Since the kinetic energy of these particles does not change, the temperature of the substance remains constant. So it's not kinetic energy that's being affected, it's potential energy. So it's almost like it's hidden, and that's where this comes into play. Latent heat. Kind of a word that describes hidden. So as you have learned, when a substance absorbs or releases thermal energy during a phase change, the temperature remains constant. The absorbed energy or released during a change of state is called the latent heat. We also use Q to symbolize it, of the substance. And of course the word latent means hidden because there's no change in temperature. So it's like we're adding heat or removing heat, and yet the temperature is not changing. Where is it going? Well, it changes in latent heat. This thermal energy remains hidden until the opposite change of state occurs. For example, thermal energy absorbed when ice melts into liquid remains in the liquid water until it is released when the liquid freezes back into ice. Latent heat is also measured in joules. Every substance has a latent heat of fusion. Remember, fusion is the same thing as melting. And a latent heat of vaporization, which is evaporization. The latent heat of fusion is the amount of thermal energy absorbed when a substance melts or released when it freezes. Note that these energy values are the same for a particular substance because the amount of energy absorbed when a solid melts into a liquid is the same as when it's released when that liquid freezes back. We use the term latent heat of fusion for both, whether we're melting or freezing, because it's going to be used. The only difference is that sometimes it's added, sometimes it's removed. The latent heat of vaporization is the amount of thermal energy absorbed when a substance evaporates or released when it condenses. As this latent heat of fusion, the energy values required to cause the substance to evaporate or condense are the same, but again, the signs could be different, whether it's being absorbed or released. The specific latent heat of a substance is the amount of thermal energy required for 1 kg of the substance from one form to another. Every substance has a specific latent heat because every substance is composed of different atoms and molecules which can absorb and release differently. The specific latent heat of fusion, symbolized LF, is the thermal energy required for 1 kg of a substance to melt or freeze, and the specific latent heat of vaporization, symbolized LV, is the thermal energy required for 1 kg of substance to boil or condense. The SI unit for specific latent heat is in joules per kilogram. The value for many specific latent heat of fusion and vaporizations are on the next page. All right, so here you have some values. So these are ones that we're going to be using in the course. So for example, water melts at 0, boils at 100. So you have melting point and boiling point. Also, latent heat of fusion, latent heat of vaporization. So you can compare those values with one another. And remember, those latent heat values are the joules required for 1 kg. So of course, a lot of times we don't have 1 kg. We have more than 1 kg. So the equations here are very easy. If we have more than 1 kg and we want to figure out how much energy is absorbed when something melts, such as water or lead or gold, we just simply take our LF value, our latent heat of fusion, and multiply by the number of kgs we're dealing with in this case. Or if I want to look at latent heat of vaporization, take the number that is absorbed for 1 kg and multiply by the number of kgs I have. All right, so this is kind of the first part of 1.4. In the assignment, you should be able to do questions 1 to 5 at this point. And then we'll come back and do the calculations. So 1 to 5 are kind of the qualitative type questions, and then the next part we'll look at actually doing calculations. All right, see you again.